All right. Welcome to lecture 3.9. In this lecture, we're going to talk about how to determine if two variables are associated when one of them is categorical and the other one is numerical. This is the last bit of new information, by the way, in this class. We will have one more section, but it's just going to be a review of the Chapter 3 material. And even this section doesn't really contain anything new because we're just going to be talking about sort of reframing mean tests as independent tests. So there's no new hypothesis testing here, but we're just going to be talking about the tests that we already know in terms of independence. So starting in Section 3.6, our goal has been to investigate whether two variables have a dependent relationship, right? If there's some kind of association between them. And so far, the types of comparisons that we've looked at in detail have been the association between two numerical variables, which we talked about in Section 3.7. And then we've also talked about the association between two categorical variables, and that was in Section 3.8. So in this section, we're going to talk about what to do if one of your variables is categorical and the other one is numerical. And for those, we're going to run either an ANOVA or a two-sample t-test, right? So we're going to be comparing means, basically, for those kinds of samples. But we're going to reframe those in terms of hypothesis tests. So let's get started. So suppose that we want to study whether a student's test score is affected by where they sit in class. So we might go around and ask students where they sit, and then ask them where their last test score was, and then we might collect the data into a table kind of like this, right? Now the question is, what hypothesis test should we run here? And what we would want to do is we would want to know what the average test score was for people who sat in the front versus the average test score for people who sat in the middle versus the average test score for people who sat in the back. And that would tell us, right, if people who sit in the front, for example, have a larger average test score than people who sit in the back, then that would tell us that, yeah, where you sit in class will affect your test score, okay? So the hypothesis test we would run here, since we're comparing three means, would be an ANOVA, right? We'd run an ANOVA, right? Our null hypothesis would be mu1 equals mu2 equals mu3. And the alternative, of course, would be that at least one of the means is different. Now, again, a common misconception here is that the variables we're comparing are front versus middle versus back, but that's not accurate. Those aren't variables. Those are just the categories. Those are the categories within the categorical variable of position in class, right? So front, middle, back are not the variables that we are comparing. The variables that we're comparing are position in class and test score, right? So the variables we're comparing are position in class, or maybe we can call it the seat position would be better. Seat position versus test score. Okay, those are the variables that we're comparing. Front, middle, back are just the possible responses to the seat position variable, okay? So then how would we state these hypotheses in terms of independence? Well, we would say the null hypothesis is that seat position and test score are independent. Okay, and the alternative would be that they're dependent, right? Seat position and test score are dependent. Okay. Now, another way that we could have recorded our data. Okay, so again, we were trying to discover if test score and seat position are somehow related to one another. And we said originally that, we could collect our data and record it this way. But another way that we could have recorded our data would have been to just keep track of each individual and whether they said that they sat in the front, back, or middle, and then their test score, right? So we could have recorded the data this way. In fact, in most data sets, this is going to be the way that the data will be recorded. The nice thing about having the data this way is that then it becomes very clear, right? It's much more clear that the variables that we're comparing are seat position and test score, right? And you can see here that seat position is obviously a categorical variable and test score is obviously a numerical variable. And so it becomes very clear that, okay, when I'm comparing two variables and one of them is categorical and the other is numerical, then I should compare the means, right? I should break down the numerical variable by the responses for the categorical variable and then compare the mean of like students who sit in the middle versus students who sit in the front versus students who sit in the back, right? So with that said, as nice as it is, as clear as it makes it to have the data stored this way, in order to actually run any analysis, we have to do that splitting up, right? We have to split the test scores by seat positions in order to do anything useful, right? So if we want to compare sample means or make box plots or run an appropriate hypothesis test, we have to take the raw data and split it, right? We have to split it so that it looks the way that it did when we first looked at this example, right? Now, the hypothesis test we end up running depends on how many columns we end up with after we split our data. Here we have 3 columns, which tells us that we're going to be comparing 3 means, so we should run an ANOVA, right? If the split data contains 3 or more columns, then we'd run an ANOVA. But it could be that your categorical variable only has 2 possible responses, and in that case, you're only going to end up with 2 columns when you split up your data, in which case it would not be appropriate to run an ANOVA. We wouldn't run an ANOVA when we're only comparing 2 means, right? So in this example, we're looking at handedness versus test score, right? Is your test score affected by whether you're right or left-handed? There are only 2 possible responses in the handedness column, and so you're only going to end up with 2 columns when you split the data, okay? And consequently, you're only going to be comparing 2 means. So you shouldn't run an ANOVA on that. You should run a 2-sample t-test. So in this case, we would state our hypotheses in terms of independence in a similar way, right? We would say handedness and test score are independent. And then I don't have room to write it down, but the alternative would be that they're dependent, right? So we would write it the same way, but this time instead of writing an ANOVA, right, we're not going to run an ANOVA because there are only 2 categories. We're going to run a 2-sample t-test. Okay, and that 2-sample t-test is going to be 2-tailed, right? So if we were writing the hypotheses in terms of means, we would say mu left equals mu right, okay, versus mu left not equal to mu right. All right, that's the test we would run. Okay. But we're going to state the hypotheses in terms of independence if the question that we're trying to answer is whether or not the variables are independent. Okay, so let's do a couple examples. This one says, a professor collected information about the students in his class. The data can be found in the Data for 3.9 Excel workbook, so you'll need to have that Excel workbook downloaded so that you can follow along with the examples. It says, compare the following pairs of variables. Make a box plot, run an appropriate hypothesis test at the 0.05 level of significance to determine if the variables are independent. So in part A, we want to determine if seat position is independent of homework score. Okay, so, all right. So the null hypothesis is that the variables are independent. The alternative is that I'm just going to use little ditto marks. The alternative is that the variables are dependent. Okay, to run the test, well, to know which test to run, actually, we need to know how many possible responses there are in this to the seat position variable, since that's our categorical variable, right? The homework score will be a numerical variable, so that's the one that we want to split. So I think this is as far as we can take it until we have a little bit more information about how many categories there are for seat position. Based on our on the previous example we were looking at, I would say that there's probably 3, right? Front, back, middle, but we have to make sure of that. So let's head over to Excel. So this is the data set in question. We've got shoe size, homework score, test score, whether or not they took a practice test, their handedness, and then their seat position in class. And sure enough, it looks like we've got middle, front, back. So it looks like we're going to be running an ANOVA here. Okay, so if what we want to do here is compare homework score to seat position in class, then we're going to need to split up the homework scores by the position in class. So in order to do that, what we're going to want to do is sort this data set by seat position, and then we can copy and paste the homework scores into separate columns. So let's do that. We've done this before. So I'm going to go to sort and filter and do a custom sort. I want to sort by seat position in class. So now this will put all of these values in order, okay? And so I can make my columns back, back, middle, and front. And I can copy and paste the homework scores for people who sit in the back of the class. So I'm going to keep scrolling until I get to the back. So that's that one right there. And I'll just copy and paste. We'll do this for the middle. Oh, we've got the front next. That's fine. Ooh, did I miss one of the backs? Yeah, I stopped it. I stopped too early, right? I need this one in the back as well. This individual sits in the back. So I should put 66.28. Almost missed one. Okay, but then the fronts start here. So I'm going to grab all of these who sit in the front. There we go. Copy. And let's put them in the front column. And then middle should be all the way at the bottom. So I'm going to grab all the people who sit in the middle. Or the test scores of the people who sit in the middle. So copy and paste. And what I can do now is, compare the average of these people. I can also make a box plot. I'm just going to go ahead and make the box plot because the box plot will show me where the average is anyway. So I'm going to insert a box plot. And the X in the box plot shows me what the averages are. They look fairly similar, especially the orange and the green, but I wonder what orange and green represent. Let's add a legend. Okay, so orange is middle, green is front, blue is back. Okay, so it looks like the average test score might be slightly lower for the back. Let's see, if I hover my cursor over that, that's about a 67.7. And here we get a 72.1. Here we get a 71.9. So those are fairly similar. I don't know if we'll see a difference, but the only way to know is to run an ANOVA. Okay, so we'll run an ANOVA test to see if those differences in means are statistically significant, right? So let me go ahead and copy my data from the back row, and I'm going to paste it into an ANOVA test. So copy, and let's come over to Art of Stat. In the web apps, I want to run an ANOVA, so I'm going to scroll almost all the way down. The ANOVA test is this app right here, so I'll open that up. And I'm doing my own. I do have 3 groups here. Group 1 was back. And there's the data. Okay. Group 2 was middle, and group 3 is the front. Okay, so let's grab the middle. And let's grab the front. It's okay, by the way, that the sample sizes are not all the same. You can still run an ANOVA on that. If I want, I could look at a box plot, or I could look at histograms of these things. So that's all kind of nice. I already had the box plots to begin with. And yeah, look at these sample means. They're pretty similar. This one is a little bit less, but it's not statistically significant, okay, because we get a very large p-value here, 0.7017. Okay, so let's write that down. We ran an ANOVA, right? We went to Art of Stat, and we went to ANOVA. Okay, one way. The hypotheses that we were really kind of looking at for the null hypothesis here was that the mean of people who sit in the back is equal to the mean of people who sit in the middle is equal to the mean of people who sit in the front, right? That's kind of how we set up our ANOVA. And the p-value we got was 0.7017. Zero 0.7017 is not less than 0.05. So we do not reject the null hypothesis. So there is not sufficient evidence to indicate that seat position and test scores are dependent variables. Okay, there's not sufficient evidence to say that they're dependent. So apparently it doesn't matter where you sit in class. Okay, it's not going to affect your homework score. Very good. Let's look at the next one. Part B wants us to compare practice test versus test score. Okay, so we want to know if practice test and test score are independent, or if maybe there's a dependent relationship between those variables. Now here it's not super clear. When we say practice test, what are we talking about? Are we talking about the score on the practice test? Or are we talking about whether or not they took the practice test? We'd have to look at the data to know. And so we'll do that in a second. If we're comparing a practice test score to a real test score, then we wouldn't run an ANOVA on that, right? Because then we'd have a numerical variable versus a numerical variable. So we would run a linear correlation test. But if practice test is just filled with like, yes, I took the practice test, or no, I didn't take the practice test, or something like that, well, then we would run an ANOVA, right? We would split by their response to whether or not they took the practice test. So let's take a look at what we've got. I'm going to delete our work from the previous problem. Delete all these rows. Okay, we're looking at test score versus practice test. And yes, it looks like the answers to practice test are either yeses or nos. So I think we're only going to be comparing two means here, right? We're going to be comparing the average test score of people who said no to the average test score of people who said yes. So let's select our data, and we will sort, do a custom sort. This time we want to sort by whether or not they took the practice test. Okay, and now I can take the test score of people who said no. So let's make our columns no and yes. Okay, and I can take the test scores of people who said no, copy, paste, and then the test scores of people who said yes, copy, and paste. And then once again, I could calculate the sample means of these two columns by typing in equals average, and then selecting the data. But since I will get the sample means by making a box plot anyway, I might as well just look at the box plot. And let's add a legend so I know which group is which. Okay, so if you take the practice test, this does look like a significantly different outcome to me. Notice that the median of the group who took the practice test is as large as the third quartile of the group who did not take the practice test. As for the actual means themselves, the average for people who took the practice test was about a 75.4, and for people who did not, it was a 61.72. That's a large difference. That's the difference between passing and failing, right? Yeah, it's like a 14% difference in test scores. So that's pretty large. I would imagine that it's statistically significant, and we would also say that it's practically. I would say there's a practical significance here, like a pretty big practically significant difference as well. But the only way to know for sure what the results of the test will be to run the test. So let's select our data, copy it. Now, I'm not going to run an ANOVA this time because I'm only comparing two means. The app will allow you to run an ANOVA, but you shouldn't. You should compare two means, right? You should use this app here. You'll get a better p-value this way. Let's we won't use summary statistics. We have our own data actually. So this is no, and there was the data. And then group 2 is yes. The name of our response variable is test score. Right? Okay, so let's copy and paste the yeses. Oh, here comes my dog. So you're going to start to hear snoring soon. Copy and paste. And we're getting a confidence level for the difference. You can see that 0 is not included in this interval, which means that we're going to be rejecting the null hypothesis for sure, but we can click on significance test to get the p-value if we want. Notice though that at least the difference is a 5, like we're 95% sure that there's at least a 6% difference in test scores, if you take the practice test versus if you don't. So yeah, p-value 0.0007. Look at our sample means here. All right, standard deviations, they give us a box plot. Okay, let's write down our p-value. So we went to, so maybe I should say, really the way that we're setting up our hypothesis test here, right, is we're comparing the means of, actually we did the no's first, right? So we're comparing the means of the people who said no to the mean of the people who said yes, and we're running it two-tailed, right? So this is just a two-sample t-test. We went to art of stat, and we went to the compare two means. And in case there's any confusion, we're using the independent case, because remember we have a dependent test for means, but we're using the independent test, right, where the samples are independent of one another. That's the app that you should be running. Okay, our p-value 0.0007. Okay. So 0.0007 is definitely less than 0.05. So we reject H null. Okay, so there is sufficient evidence to indicate that practice test, and I'll put a little question mark there to kind of remind us that this was a question, right? Did you take the practice test, yes or no? So there's sufficient evidence to indicate that practice test and test score are dependent. Okay, now we could make a stronger conclusion in this case, because your test score is not going to retroactively determine whether or not you took the practice test, right? Because you would take the practice test before taking the test. So really the logic flows in the other direction, right? It's that whether or not you took a practice test will affect your test score. And to be even more specific, we can see from the sample means that if you take a practice test, you're far more likely to do better on the test, right? If you take a practice test, your test score increases by like 14% on average, okay? So that's a substantial difference. Okay. One more topic that I want to talk about in this section has to do with the way that that all of this raw data looks in like a big data set. It could be the case that you have two numerical columns that you're looking at in a data set. And what we've talked about before is that if we want to explore whether there's an association between two numerical columns, then we would run a linear correlation test. And this is true if what you're trying to do is determine if the columns are correlated, if you're trying to determine if there's an association between the variables in those columns, right? If the responses in one column affect the responses in another one. But this may not always be what you're trying to do with two numerical columns. Okay, let me give you a couple examples. Okay, so for example, suppose that we ask a group of people how old they are, and then we ask them how old they wish they were. Okay, so you might end up with two columns in your data set, one for their actual age and then one for their desired age. Now, if we want to know whether people generally wish that they were younger, a linear correlation test would not work for that, okay? Because if you run a linear correlation, and here I'm going to ask you to use your imagination a little bit, but let's say that you want that you run a linear correlation test. Let's just pretend for a moment that the numbers in the actual age category and in the desired age category are perfect matches. Let's just say that everyone is perfectly happy with their age. And then you run a linear correlation test, right? To see if actual age and desired age are correlated. The answer to that question is going to be yes. There's going to be a perfect linear correlation because everybody is perfectly happy with their age. But that would not answer the question of whether people wish that they were younger, okay? Because let's imagine now that everybody's desired age, let's just imagine that everybody's desired age is like 10 years younger than their actual age, okay? If that were the case, then once again, we would get a perfect linear correlation, okay? We would get a perfect linear correlation. So you're going to get a perfect linear correlation whether or not there's a difference between these variables, assuming that people you know, say that their desired age is somewhere within the same ballpark as their actual age. All right. So let me say that again. Right. If people's desired age is somewhere in the same ballpark as their actual age, then you're going to see a linear correlation between actual age and desired age. That does not answer the question of whether or not people wish that they were younger than they actually are. Okay? So in order to so let's write down. So I'm asking, a linear correlation test would not work. Why not? Well, the linear correlation will only tell us if people if people are more or less happy with their age, right? It won't tell us if the average desired age is less than the average actual age. Okay? So if our goal is to determine whether people generally wish that they were younger than they are, what test should we run? Well, what we would want to do is compare the average actual age versus the average desired age. If the average desired age is like 5 years less than the average actual age, then we would conclude that, yeah, people tend to wish that they were younger than they actually are. Okay? So we should run a 2-sample t-test, right? Specifically, we would want to run this test. We would want to know if the mean of actual age is equal to the mean of desired age, or if the mean actual age is perhaps greater than the mean desired age, right? Because we want to know if the mean desired age is less than the actual age. Okay, so that's the test that we should run. Now, suppose, on the other hand, that we ask a group of people for their height and their shoe size. If we want to know whether shoe size is affected by height, why would it not help us to compare the means of these two columns? Okay, why would we not run a 2-sample t-test in this case? Well, because you could take the average height and you could take the average shoe size and you could compare those means, but it's not going to tell you anything. Okay, because you're not comparing apples to apples. Height, the heights are of course always going to be bigger than the shoe size, right? Your height, I would hope that you're taller than your feet are long, right? I would hope that your feet are shorter than you are, if that makes sense. So comparing the average height to the average shoe size is just not a helpful comparison, right? What we want to do is we want to see if if increasing somebody's height will cause an increase in their shoe size, which I think would be a reasonable assumption, but that's what we would want to test, right? So if what we want to know is whether shoe size is affected by height, it wouldn't help us to compare the means of these two columns. Why not? It wouldn't be helpful because the average height is obviously going to be more then the average shoe size, we are not comparing like things. Right? So we don't want to compare their averages. What we want to know is whether they're correlated, right? What we want to know is not whether the numbers are equal, but rather whether the numbers are correlated. So what test should we run here? Well, here we should run a test for independence, right? We should say our null hypothesis should be that height and shoe size are independent. And the alternative should be that those variables are dependent. Now in this case, since height and shoe size are both numerical variables, the way that we run that test is by doing a test on the correlation coefficient, right? We would be testing to see if rho equals 0 or if rho is not equal to 0. Okay, so we'd be running a linear correlation test, right? Whoops. Okay. So the takeaway here is, if we want to compare two numerical columns to investigate whether the responses in one might affect the responses in the other, then we run a linear correlation test. If we want to compare two numerical columns to see if the average value is different in each column, then we run a matched pairs t-test. Ooh, and I might need to make sure that... okay, yeah, I called it a two-sample t. We want to make sure it's a matched pairs t, actually, because we would in this situation have matched pairs, right? Each individual, each individual's actual age is a matched pair with their desired age. So we would run a matched pairs t-test. So make that correction. Right? So we would run a matched pairs t-test for this. Okay. So yes, if we want to compare, if we want to see whether one column affects the other, then we run a correlation test. If we want to see if the average value in one column is different from the average value in another column, then we run a matched pairs t-test. So let's just take a look at a couple of examples. So this one says a group of women over the age of 70 were asked how many children they had given birth to, how many children their mothers had given birth to, whether or not they had ever been divorced, and what their current party affiliation is. And the options for party affiliation are Democrat, Republican, or other. Excuse me. Okay, so like here's an example of the first few rows, or the first couple rows, I guess, of the data set. So part A says, if we want to test whether the number of children a woman has is independent of the number of children her mother had, what test would we run? So we want to compare these two columns, and we want to know if there's some kind of association between them, right? We want to know if the number of children a woman has depends on the number of children her mother had, right? So there we would run a linear correlation test. We want to see if the values in this column affect the values in this column, right? So we'll run a correlation test. So we'll do is number of children and mother's children independent. And I won't write down the alternative. I mean, on any of these examples, but that would be the null, right? We would run a test for independence. In terms of, it would be more specifically a linear correlation test, right? Linear correlation test, because those two variables are numerical. So we run a linear correlation test on that. Linear correlation test. The null hypothesis would be rho equals 0, right? Okay, part B. If we want to test whether this generation of women had fewer children than their mothers, what test would we run? So on part B, notice that we're going to compare the same two columns, but the question that we're trying to answer is different. In part B, we're trying to answer whether or not this column, the mean in this column, is less than the mean in this column, right? So in this case, we would run a matched pairs t-test. Okay, because each individual here is a matched pair with herself here, or a matched pair with her mother. Okay, so we would run a a matched pairs t-test. The null hypothesis we would want to run is whether the mean of we'll say C for children is equal to the mean for, we'll call it M for mother's children, right? We want to know if that, or if maybe this generation had fewer children than their mothers did, okay? And this would be a matched pairs t-test. Okay. Part C. If we want to test whether the number of children a woman has is independent of her history of divorce, what test would we run? Okay, so the divorced column just has two possible responses, yes or no. Either a woman has been divorced in the past or she has never been divorced. Okay, so if we want to know whether the number of children that she has is somehow dependent on whether she's been divorced, then we would run a test for independence. But since there are only two categories here, it's going to be a two-sample t-test. Okay, so we would state the hypotheses as in terms of independence, right? We would say, what was the column called? Divorced. Divorced. Oops. Divorced. And number of children are independent, and the alternative would be that they're dependent, right? But this time it's going to be a two-sample t-test. The null hypothesis would be that the mean of the divorced is equal to the mean of the not divorced, right? It would be a two-sample t-test. Okay, so this is where we use a matched pairs t. This is where we used a two-sample t. What about an ANOVA? Well, if we want to test whether the number of children a woman has is independent of her political party, we would run an ANOVA, because political party had three possible responses, right? Republican, Democrat, or other. So we would need to split the number of children column into three columns, right? Republican, Democrat, and other, and then compare those three means. So we would have to run an ANOVA on that. So what test would we run? Well, we would state it as a test for independence. Okay, we would say political party and number of children are independent, okay, and then the alternative would be that they're dependent. This is going to be an ANOVA though, because we would compare, is the average number of children for a Democrat the same as the average number of children for a Republican? And is that the same as the average number for somebody who belongs to some other party? Or are maybe they different, right? And so we would run an ANOVA test because we're comparing three means. Okay, so we know what to do when the columns that we're trying to compare are both numerical, right? We run a linear correlation test. We know what to do if the columns that we're trying to compare, one of them is categorical and the other one is numerical. That's when we would run an ANOVA or a two-sample T. Okay? If they're both categorical, like if we want to compare whether or not, being divorced is independent of your political party, well, for that we would run a chi-square test for independence. Okay, so if we want to test whether a woman's history of divorce is independent of political party, what test would we run? We would state the hypotheses in terms of independence, right? We would say political party and divorce are independent. Okay, the alternative would be that they're dependent. And I'm not going to try to write down what that would look like in terms of, well, we could. So it would be a homogeneity of proportions test. We would want to know if the proportion of Democrats who are divorced is equal to the proportion of Republicans who are divorced is equal to the proportion of independents who are divorced. Or we just called it other. So is equal to the proportion of others who are divorced, right? But here we would run a chi-square test for independence. Okay, so that one's just for good measure, but those are the kinds of tests that we would run if we were trying to explore the relationships between variables in a data set. Okay, and again, kind of the main purpose of this section was just to kind of point out the difference between part A and part B, where in part A, if you're trying to determine if the variables are correlated, well, then you run a linear correlation test. But if you're trying to determine whether the average in this column is different from the average in this column, then you would run a matched pairs t-test. Okay, so that'll do it for this section, and we'll check in with you in the next one.